Okay, your question set we'll be reviewing today is 65 to 70 on the CSTs. And again, the CST question numbers are right down here. In this first problem, we are doing acid-base pH. And so it helps to look in the textbook on page 611. And so let's go there together. And on page 611, you see this graphic, and I've written some things onto it. First of all, if we look right up here, we see pH plus pOH being equal to 14. Now, the pH is the minus log of the hydrogen ion concentration, and the pOH is the minus log of the hydroxide ion concentration. This formula, in conjunction with this formula, are going to be used a whole lot in your homework problems, as well as in the CSTs. So the K sub W is the equilibrium constant of water for its self-ionization. And that was part of our lesson in class today. So if we look at a pH example that I have listed down here of 2, we see that pH plus pOH is equal to 14. So we look here on this chart and we see that the pH is 2, the pOH is 14. Or, I'm sorry, is 12. And together they add up to 14. So this chart, you're seeing the hydrogen ion concentration all the way across, and the hydrogen ion concentration is getting smaller as that negative number gets bigger. Also, the pH is getting bigger because pH is the minus log of these numbers. The log of 2 minus that is minus 2. So the log is just the exponent in a base 10 system. So the exponent here is minus 2, so when I take the minus log, that is also a minus 2. Minus 2 times a minus, which makes it a plus. That's why pHs are always going to come out positive, almost without exception. Once in a while you get a negative pH, but that's very, very rare, and you're unlikely to run into them in the CSTs. So here we go with now the K sub W is always going to be equal to, and I haven't written that in, let's go ahead and finish that off, is always going to be equal to a 10 to the minus 14. And as you will see in my example, when we come over here and now we deal with concentrations of hydrogen ion, we've got a 2 for the hydrogen ion concentration, that's this 10 to the minus 2, and we got a minus 12 for the hydroxide ion concentration, which is this. So the hydroxide ion concentration times the hydrogen ion concentration is what we're seeing here and here. So when we multiply powers of 10, we add them. And adding these guys makes them come out to a minus 14, as it should. And notice you will add 10 to the minus 7, 10 to the minus 7, you get 14. 10 to the minus 11, 10 to the minus 3, 14. 10 to the minus 13, 10 to the minus 1, 10 to the minus 14 again. Always going to be that way. And the pHs here and here that I was doing from this formula always add up to 14, not 10 to the minus 14. It's not a minus because it's a negative log, and it's not an exponent because we have logged 10 to the whatever. And this is where these numbers come from. So the pH goes from 0, most acidic, to 14, which is the most basic. And when we go either side of 7, we go either acid or we go base when we go this way. Now pH is exactly the opposite, as you would expect it to be, because these guys are added to get 14. So pOH is the largest number of POH is actually the smallest number of the pH, which is 0, and those two added together come up to 14, as they should. So POH is getting smaller and smaller and smaller, and the hydrogen ion concentration is also getting, hydroxide ion, I'm sorry, we're down here on the bottom. Hydroxide ion concentration is actually getting bigger, where the hydrogen ion concentration is smallest here and largest here. They're exactly backwards from each other. So here we have increasing basic, going from neutral to here, we have increasing acid. And now we can intelligently answer the question. So the question says, who is, as we read it up here, our laboratory different solutions, solution with the highest acidity is actually the smallest number. So 3 here is our answer, as you will see on my answer key. And 3 goes to 5, less acid, bigger number, less acid, not acid at all, but actually neutral, and now we're into the basic range. So that's how this little guy works, and I needed all the rest to explain that to you. Moving right along here, next question up is, now in question number 66, it's asking us which of these describes the rate of chemical reaction. Now the rate is included with the word time. So you'll notice time in all of these. So let's go ahead and see, in describing the rate, we must also note that the reaction goes from the left, where the reactants are, to the right, which is where the products are. And so the word rate is included in the word time, as I was just describing. What is even more important is that hydrochloric acid, the HCl, will increase because it is the product. And only answer C shows us that. It includes both a reference to the rate as well as HCl as the product, which will increase with the forward reaction. So an increase in the concentration of HCl with time is what is going to happen, okay, with this reaction. And that's all there is to this one. Going on to number 7. The catalyst is irrelevant in this question. And up here I just gave you a description of catalyst which you can read. Decreasing the temperature. Now you see this is a Le Chat problem. So decreasing the temperature has no effect because we don't see exo or endo. We don't see heat. We don't see delta H. None of that stuff's there. So Le Chat isn't going to be able to do anything, because he hasn't been blessed with the ability to do it in this reaction. Now, in letter B, we are decreasing the C6H6. Now, Le Chat has to shift to the left to make more. See, when we decrease decreasing the concentration there, we are actually going to bring this guy down, and Le Chat wants to bring him back up. And to do that, he has to make these guys the reactants and move the thing this direction. And that's counterproductive to what we want. And then in C, increasing HBr, Le Chat wants to decrease it. And it will decrease as he shifts it to the left, putting this and this together to make these guys. So that doesn't work. And then the one that does actually work is increasing the concentration of bromine. So if the bromine is up, it will cause Le Chat to shift to the right. Why? Because to get rid of this guy, which is what he wants to do because we put more in, he has got to put this together with this to make these two. And that's why that is the correct answer. And moving on, our next question. If the reaction below takes place inside a sealed chamber, and when we have a sealed chamber, that means that we're going to be having a pressure situation. And they are going to decrease. How are we going to decrease the rate of reaction? I have the arrow here to say we want whatever we do to make the reaction go this direction, and that will decrease the rate of the reaction as written, which is moving to the right. So we want a left shift. Now when we remove carbon monoxide, Le Chat wants to make more. And if we look at our answer here, the answer is letter C. So why don't we do that one first? Let's go ahead and increase the volume inside the reaction chamber. When the volume goes down, as you can see here, the pressure will go up because these guys are inverse. So increasing the volume inside the reaction chamber actually made the pressure go down. Now, this is a situation where with pressure and volume, we have to look at the moles on each side. So let's add them up. On the left side, we have this 2, and that makes 2 moles. And this guy, the coefficient is actually a 1, so that's 2 plus 1 is equal to 3 on the left. On the right side, we only have the 2, so 2 is our total on the right, 3 is our total on the left. So to reverse this thing, we want the pressure to go up, and to get the pressure up, we go to the side with more moles, and that's why we want to go to the left to increase, and that is the direction that I originally set this thing to, which is what we're trying to accomplish, and we needed Le Chat to help us. So that's why letter D is your correct answer. And work it out, the other guys will all take you the other direction. Moving on to number 9. I've described this pretty completely. Your answer is, in this case, letter A, and let's see why that one is correct. A catalyst can speed up the rate of a given chemical reaction. And the question is, how? And in this question, you have to be sure you're responding to the question. The question is, how can we speed up the rate of a given chemical reaction? Lowering the activation energy required for the reaction to occur. The way a catalyst works is by lowering the activation energy. And the activation energy you will see in a prior chapter. Moving on, which reaction diagram actually shows the effect of using the appropriate catalyst? This guy is the winner, and if you look at my key, I'm sorry, whoa, I've got the key wrong. So, now the key is correct. So that'll show up right in the future. Anyway, going over here to letter A, after the catalyst, the energy of activation, or the hill that we have to get over, is a lower hill. We can't move forward till we get enough energy to actually get up. See, energy is going up this direction. That's what you see in here. Okay, so we have to get enough energy just to get up to here, as opposed to having to get way, way up here. So reactions that wouldn't go at all will actually start going very vigorously if we add a catalyst. And we will have a demonstration in class about that. I call it elephant toothpaste, but this is a fun deal to watch. And catalysts, you can look on page 534 to get a little bit better background on that in the text. That's it for this guy.